Hi, I'm Syam. I'm representing Group 3 for a CS263 paper presentation. We are here to present BART. It is a denoising sequence pre-training for natural language generation, translation, and comprehension. BART in its expansion gives you bidirectional autoregressive transformer. The name comes from its architecture itself, which I'll be discussing as we move forward. The main component of BART consists of a denoising autoencoder for pre-training sequence model. It is trained by taking the original document that has a number of that has text information and using an arbitrary noise function to convert that original text into a noisy text. And we create a model to learn how to reconstruct that noisy text into original text back again. So it uses standard transformer-based neural machine translation architecture, which consists of two components, BERT and GPT. And these two components are something that you already seen in class. The evaluation for the best performance happens by using different noising approaches. A couple of them are random shifting the order of the original sentence, and the other one is infilling schemes, wherein you take a text word and you infill with a masking token, which spans or masks a span of characters. It is best used for text generation and comprehension tasks. So the overview of the architecture consists of two components, as I told you before. It has an encoder and a decoder, and it is very important to emphasize on bidirectional encoder and left to right decoder. Here, bidirectional means it can understand the context in both the directions, whereas in the decoder, it generates new text having the context of the concept of the characters it has seen in the past. Characters or text it has seen in the past. Here, the encoder takes in the input of A _ C _ E. Let's assume that the corpus has A, B, C, D, E. Here, the encoder generates B by seeing A and D by seeing C. Similarly, for decoder, the input sequence is a start token A, B, C, and D. So it generates E by understanding the sequence A, B, C, and D, because E is the obvious next character after D. So combining these two, an encoder and a decoder, gives you the BART architecture. And for pre-training, we optimize using negative log likelihood loss of the original document. So we have seen about this previously, wherein we have a sequence-to-sequence model that uses RNNs. RNNs obviously are not that favorable because of the vanishing gradient problem. Then we came up with LSTM. LSTM did fix the vanishing gradient problem, but it was not able to, it only accept input in a very sequential way. It can't achieve parallelism. And that's one of the reasons why we went on with the transform-based architecture, wherein the word embeddings of the entire sentence, each word in the input sentence, its embedding can be generated parallelly, right? So consider an example wherein you'll have to translate English to French. Here we have an encoder and a decoder part. And let's say this is amazing is the input text. Each word in this input text is being considered into embedding vectors parallelly by the encoder. And for the decoder part, each and every token is being generated one after the other by considering the context of the previous token. Here we have the start token as the starting token, which gives you Sissy, which is this for French, which gives you A, which is for French, and which gives you incroyable, which is amazing in French. Okay? So by combining all those, you get the output of converting an English sentence into a French sentence. If you think about it, the encoder and the decoder separately has its own function, right? So encoder understands what is English to a certain extent, and it understands the context of different words in a single sentence. Whereas the decoder, on the other hand, identifies or knows how to map English words into French words. So if you stack multiple encoders one after the other, that gives you the BART architecture. And if you stack multiple decoders one after the other, that gives you GPT. This is pretty much self-explanatory from the name, which says bidirectional encoder representation from transformers. So we just take the encoder, stack it one on the other from the transformer. And even though the architecture is very similar to something that we have already seen, BART has some tweaks to the existing architecture. One such tweak is, even though it's closely related to BERT, each layer of the decoder additionally performs cross-intention over the final hidden layer of the encoder, which means that unlike BERT, which just takes the output of the encoder into the single layer input, it just takes it to the input for all layers in the decoder. And also the feed forward network, which is present in BERT, is not present in BART. Additionally, in the GPT, when we use ReLU activation function, here we use GELU, which is Gaussian error linear unit, and we initialize the parameters using a normal function, a normal distribution with 0 and 0.02. The layers for the base model are 6 layers, and for large model is 12 layers for both encoder and decoder. And the BART contains approximately 10% more parameters than its equivalent BERT. Now I'll hand it over to Auroswetha to continue with the fine-tuning and phase.
Thank you, Syam. Now we'll talk about pre-training and fine-tuning in BART. So in this, BART is being trained on minimizing reconstruction loss on the document created from the original document. To ensure model robustness, we are imputing different type of noise to train it with different possible use cases. As you can see in the figure, we have a corrected document which is being reconstructed and then compared with the original document. So to corrupt the documents, we have different types of transformation or noising. So the first one is token masking, where random tokens are sampled and replaced with elements. Then we have token deletion, where random tokens are deleted from the input. Then we have text infilling, where number of text spans are sampled with span lengths drawn from Poisson distribution. Each span is replaced with a single mask token, and zero length spans correspond to the insertion of mask tokens. Then we have sentence permutation. A document is divided into sentences based on full stop, and these sentences are shuffled in a random order. Document rotation. A token is chosen uniformly at random, and the document is rotated so that it begins with that token. Then we'll move forward to fine tuning. So we'll be discussing 4 types of fine tuning. One is sequence classification task, token classification task, sequence generation task, and machine translation. So the first one being sequence classification. As depicted in the image above, the same input is fed into the encoder and decoder, and the final hidden state of the final decoder token is fed into new multiclass linear classifier. This approach is related to CLS token in BERT. However, authors have added the additional token to the end so that representation for the token in the decoder can attend to decoder states from the complete input. Then we have a token classification. So for token classification task as well, referring to the same image, they feed the complete document into the encoder and decoder and use the top hidden state of the decoder as a representation for each word. This representation is used to classify the token. Now, coming to the sequence generation, BART has an autoregressive decoder as discussed by Syam. It can be directly fine-tuned for sequence generation tasks such as abstractive question answering and summarization. In both these tasks, information is copied from the input but manipulated, which is closely related to the denoising pre-training objective. Here, the encoder input is the input sequence and the decoder generates output autoregressively. Then coming to the machine translation, in this paper, authors have used BART to improve machine translation decoders for translating into English. Previous experiments have shown that models can be improved by incorporating pre-trained encoders, but gains from this using pre-trained language models in decoder have been limited. Authors have used the entire BART model, both encoder and decoder, as a single pre-trained decoder for machine translation by adding a new set of encoder parameters that are learned from bit text. More precisely, as you can see from the figure, they replace BART's encoder embedding layer with a new randomly initialized encoder. The model is trained end-to-end, which trains the new encoder to map foreign words into an input that BART can denoise to English. The new encoder can use a separate vocabulary from the original BART model. They have trained the source encoder in 2 steps. In both cases, backpropagating the cross entropy loss from the output of the BART model. In the first step, they freeze most of BART parameters and only update the randomly initialized source encoder, the BART positional embeddings, and the self-attention input projection matrix of BART's encoder first layer. In the second step, they train all the model parameters for a small number of iterations. Now I request Shrey to continue the presentation.
Now we will compare BART with the different base size models. Each of these models has been pre-trained using the following objectives. We have the language modeling objective, wherein left to right decoders are used to generate text autoregressively. We have the permuted language model wherein tokens are generated in a random order. This is similar to ExcelNet, but there is some difference since it does not include architectural improvements like segment level recurrence and relative position embeddings. We also have masked language model wherein 15% of the tokens are masked and the model is then trained to predict the original tokens. We have the multitask masked language model, which is similar to the MLM, but the difference is that it includes multiple self-attention masks. Last but not the least, we have a mask, the masked sequence to sequence model, wherein we mask a span of 50% of the tokens. And then the sequence to sequence model is trained to predict these tokens. And this includes both the encoder and decoders. So we've now seen the pre-training objectives. Let's have a look at the tasks on which the models are going to be fine-tuned. So we have the Stanford question answer dataset task. In this, question and a context is passed as an input to the model, and the model predicts the span of the text within the context that will be the answer to the question. We have the multi-genre natural language inference, in which the model predicts whether the hypothesis is true, false, or cannot be determined based on a given premise. We have the ELI 5 task, in which the model is expected to generate simple and concise explanations of complex topics. We have the ConVI2 task, wherein the goal is to generate chatbot models that can converse with a human on a given topic in a natural and engaging manner. Then we have the XSUM and CNNDM task, where the goal is to generate informative summaries based on news articles. All the models were trained for 1 million steps on identical data, and the data was obtained from a combination of books and Wikipedia data. In order to evaluate the performance of all the models, we have used F1 score and accuracy for squad and MNLI tasks respectively, and we have used perplexity to evaluate the performance of the text generation task. Now let's see the results. So as you can see from the table, the performance of pre-training methods varies significantly across tasks. For example, you can see that the language model performs very well on ELI 5, but does not do such a good job for the squad task. We can also see that masked language models and permuted language models are not performing very well on the text generation tasks. And these are the only models that do not include left to right pre-training. So we can say that left to right pre-training improves text generation. And this is also logical because unidirectional left to right models are able to access the previous context, which is very important if we want to generate text in a natural and coherent manner. Similarly, we can see that bidirectional encoders are crucial for natural language understanding tasks such as SQUAD and MNLI tasks. And this is also logical because if a token has access to the past and the future context, then the model will be able to better understand the text as a whole. Now we will have a look at how BART performs on all these tasks. So from the table, we can see that BART achieves a similar performance as compared to bidirectional encoders on SQUAD. On the right-hand side, we can see the performance of the bidirectional encoders on SQUAD task. And on the left, we can see the performance of BART models. Also, BART is able to achieve this with half the number of bidirectional layers. And we believe that it is able to do this because of its architecture. We can see that BART achieves most consistently strong performance with text infilling. And this might be because text infilling is a complex task as compared to the other tasks, and hence it is able to capture the intricacies of the natural language text in a better way. We can also see that document rotation and sentence shuffling are not performing as well on most of the tasks. And this can be because these tasks are inducing noise in the input data, which is preventing the model from getting a good representation of the text. We can also see that ELI 5 is the only task where other models are outperforming BART. So this can be because BART is generally trained on tasks where it is encouraged to generate fluent text or understand text. It is not encouraged to simplify the generated text. So that can be one of the reasons why it is not performing very well on ELI 5. These tasks were just a subset of the large-scale experiment that Vaibhav will now be talking about.
Okay, so now I'll be discussing the large-scale pre-training experimental setup. For the pre-training, a large model was used with 12 layers in each of the encoder and decoder with a hidden size of 1024. For the pre-training, the data consisted of 160 GB of text content extracted from news, books, stories, and web text. The batch size was 8,000 and the model was trained for 500,000 steps. The tokenization used here was byte pair encoding and with coupled with text infilling and sentence permutation. The tokens in the document, 30% of the tokens in the document were masked and permuted, and the sentences were permuted. To help the model better fit the data, dropout was disabled for the last 10% of training steps. For the fine-tuning, BART is fine-tuned as a standard sequence-to-sequence model. During fine-tuning, a label smooth cross-entropy loss function was used with smoothing parameter of 0.1. During generation, beam size of 5 was used and duplicated trigrams were removed. The output was tuned with min length, max length, length penalty on the validation set. Now moving on to the performance analysis. For the first task, as we can see from this table, BART clearly performs comparably as compared to Robert A and ExcelNet, which were the state of the art for classification tasks. From this, we can infer that BART's unidirectional decoder layers do not reduce performance on classification tasks. Moving on to the summarization task. From this table, we can clearly see that BART outperforms the best previous work, which leverages BERT by roughly 6 points on the rogue metrics, which is pretty amazing. Moving on to the next slide. In here, we can see that a BART clearly outperforms on dialogue response generation, abstractive QA, and summarization tasks. For the summarization task, for the translation task, a 6-layer transformer source encoder was used to map Romanian into a representation that BART was able to denoise into English. Preliminary, the results suggested that the approach was less effective without using back translation. So back translation was used to avoid overfitting. Moving on to the qualitative analysis of the model, it was observed that BART was able to generate fluent and grammatically correct English sentences, and it is also highly abstractive with few phrases being copied from the input, which is pretty amazing for that model. Output is also generally factually accurate and integrates supporting evidence from across the input documents with background knowledge. As we can see from the first example here, the model is able to infer that fish are protecting reefs from global warming, which requires non-trivial inference, and this is pretty amazing for the model. From this, we can conclude that BART pre-training has learned a strong combination of natural language understanding and generation. So for the related work, which is the next slide, the early methods for pre-training were based on language models. Initially, GPT used to model the leftward context, which is problematic for some tasks. Elmo concatenates left-only and right-only representation, but does not pre-train interactions between these features. BART introduced masked language modeling, which allowed pre-training to learn interactions between left and right context words. It was observed that strong performance could be achieved by training for longer and by masking spans instead of words. Predictions in BERT is auto-regressive, which hampers its performance on generation tasks. Similarly, UniLM is a fine-tuned BERT model with an ensemble of mass. Moving to the mass model, which is most similar to BART. It is less effective on discriminative tasks because a disjoint set of tokens are fed into the encoder and decoder. ExcelNet extends BERT by predicting mass tokens auto-recursively in a permitted order, and it also is able to model the left and right context in the data. In conclusion, we can say that BART is a pre-training approach that learns to map corrupted documents to the original, and it is a denoising autoencoder built with a seek-to-seek model. It can be seen as generalizing BERT and GPT and allows many different ways to corrupt the document. BART is flexible for many kind of NLP tasks, such as text classification, token classification, question answering, translation, and summarization. So it's a holistic model. BART achieves similar performance to Robert A, and it achieves state of the art at that time for text generation. BART is particularly effective for fine-tuning when fine-tuned for text generation, but also works for comprehension tasks. So the future work proposed in this paper was to explore new methods for corrupting the documents for pre-training and perhaps tailoring them to specific end tasks. So yeah, this was BART.